Hello class, welcome back to Electromagnetics. This little lecture we're going to talk about Faraday's law in integral form. Inspirational thought though for the day, Romans 8:28. And we know that in all things God works for the good of those who love him, who have been called according to his purpose. So I think the thing about this verse that was pointed out to me at one time was it's not just that God causes all things to work together for good, but he does it for those who love him and those who are called according to his purpose. And so the one thing about that I may have some control over is, do I love him? And so I need to strive to nurture that and develop my love for God. We're going to continue on in part 2 of this course. So we've covered the line integral and the surface integral and kind of seen a little bit how that works with electromagnetic fields. So today we want to introduce Faraday's law in integral form. So it all starts with Faraday's experiment. So in 1831, Michael Faraday conducted an experiment that showed that time-varying magnetic fields will give rise to an electric field. So his experiment basically showed that when magnetic flux, which we've already been introduced to that, when it's enclosed by a loop, that the electric field created by this time-varying magnetic field would create a current in the loop, which translates to a voltage or an electromagnetic force. So again, if you have a loop of wire, you run a magnet through it, that's going to produce a voltage and quite possibly a current as well. So this is kind of what the setup looked like. You had these two coils of wire. So he was creating this magnetic field going in and out of this big coil of wire, which again produced enough potential voltage and or current flow that it would cause the galvanometer over here to register that there is something present. So what would this look like today? Well, if you'll go back to the Canvas page where you found this lecture, there should be a link a little bit further down that I've left there. It's a YouTube video from a professor in Purdue, and he does a makeshift version of this. It's kind of a modernized version of Faraday's experiment. It's pretty interesting. It's not very long. I would encourage you to look at it because it does demonstrate, exactly what Michael Faraday experienced when he did this experiment. So we need to talk a little bit about polarization. Polarization actually has kind of some different meanings when you talk about it in electrical engineering. But for the purposes we have here, we need to make sure we understand some definitions here. So the phenomena here can be characterized mathematically that Michael Faraday saw. However, we need to define some conventions first, is really what this is. And so this is where this polarity comes into. So in its simplest form, we can characterize this experiment 4 different ways, as illustrated below. So in these 4 different scenarios, we're going to have these loops like Faraday did. We can assume they're conductors, but they don't necessarily have to be. They're just this defined closed space here. And so you can see we're going to associate a vector with it, so we can do a line integral if we need to. So we have to associate a direction. So in these first 2, the direction is going to be clockwise. In these second 2, the direction is going to be counterclockwise. Okay, and so in all of these, we have a magnetic field present, and that's what's denoted by these X's. So incidentally, when you see a field in a 2-dimensional representation, you notice we'll either have a dot or an X. So for those of you who don't know, you need to think of it as in terms of an arrow. And so if you see the dot, that's the tip of the arrow coming towards you. If you see the X's, that's the back of the arrow where you have the feathers, I guess, that can be in the shape of an X going away from you. So you can see in all 4 of these scenarios, we're assuming the magnetic field is defined as going into the paper or into the screen. And so the only difference then between these is the area vector. So you can see in this case it's going into the sheet, here it's coming out, it's going in and going out. And so We didn't change the magnetic field, we changed the direction of our length vector and the direction of our area vector to get these four scenarios. But if we look at this for a minute, long enough, we should be able to figure out that case 1 here and case 4 are basically the same, they're just flipped over. And then again, case 2 and case 3, same type of thing. So we just need to experimentally define what's going on and what makes sense to us. And when we do, case 2 is the one that seems to define what's physically happening most accurately. And so that's the convention that we'll go with. And so what we conclude from that is the EMF, electromotive force, which is basically a voltage, is generated, and we consider it going clockwise around the loop. That would be equal to the change in time of magnetic flux out of the paper. Okay, so this is how that's defined in terms of that convention. So if we look at this just a little more, again, here's that same equation. In order to translate this into a mathematical formula, we need to apply a convention to ensure that the sign of the results has physical significance. And so again, we're going with that scenario 2. And so you can think of it as we're using that right-hand rule again, in a sense, so that, you know, the screw, which is causing the field to go through the paper, or when it goes through, the current will follow in the loop. And so that's basically what's being demonstrated here. So let's bring all this back to Faraday's law and how we can accurately describe this in a mathematical sense. So with our convention of polarization now defined, we can now develop a mathematical expression that characterizes this phenomenon as follows. And so here is Faraday's law in integral form. And so let's look at this for a minute and break it down and make sure we understand what's going on. So first, let's put it with a graph to kind of demonstrate what we're doing here. So what we have is this closed loop C. So that's the C, the circular integral we've talked about before. And so we have this surface associated with it that's bounded by C. So it's almost like if you're thinking about blowing a bubble, you know, this is the ring that the soap is in, and when you blow in it this way, it creates this bubble. So this surface is what we're talking about. And this surface can basically take any shape we want. We don't really care, and we'll even restate that later. But we just need to make sure we always have our area vector everywhere across the surface defined where it's perpendicular. That's the key to making all this work. And so we also have that this is in the presence of a magnetic field, B. So you can see the flux lines come into the circle, and then as they leave out, they penetrate this surface, you know, at various points. So this is the absolute, the ultimate generalized way to think about this. So what we're saying then is if we integrate around this circle, the E field on the circle dotted with dl, which is in the direction that it's going, this potential differential, this voltage that's created on there, is equal to the negative of the differential, or the derivative with respect to time, of the magnetic field, this B, dotted with this ds, or that's penetrating this surface. And so what that's saying is that if we could sum up this field that's coming out of this surface, out of the surface of the bubble, for lack of a better term, and it's changing with time. If it's constant, it doesn't do anything because the derivative of t would be 0. But if it's varying with time, like a sinusoid or something like that, then that's going to equal to this voltage around this loop. So that's Faraday's integral form equation in a nutshell. So as we think about this, there are a couple of things that are worth noting. The first one being, and I think I've already said it, is this equation holds for all possible surface bounded by C. You can make this surface S anything you want as long as C is what's defining it. Again, the apparatus used to blow the bubble. So the bubble can take any shape you want as long as it's still attached to C over here. The second thing worth noting here is that the loop C does not have to be a conductor. Many times people always assume it's a conductor and it's producing a current, but that doesn't have to be the case. It could be a semiconductor, it could be a insulator. It doesn't matter. This voltage or this potential to move current around or this EMF will still be there. Even though it may not generate a current, it's still going to create that voltage potential around that rim. So let's look at a couple of examples to maybe help us better understand Faraday's law in integral form. So here we want to consider that we have a constant magnetic field. So this is a little bit different, but we have a varying loop. I don't know that I've ever seen this in practice, but it is an interesting thought exercise to go through. So what does this look like? Well, we've got this magnetic field B, which again is constant. It's not varying. And so we have this wire in the presence of it. So it's almost like you have two pieces of wire here. You have this U-shaped wire that stays stationary, and then you have this solid piece of wire here that can slide up and down. It's still making contact with the other wire, but as you can see, that will change the area of the loop. All right, and so we have Y defined in this direction, X defined in that direction, and this wire is moving at some velocity, constant velocity, in the Y direction. So we've also defined this length here as L. So if we do that, the magnetic flux is then defined by, or at least the flux in this loop, is defined by the area of the loop times the magnetic field density. So how do we get that? Well, we know one side of the area is L, so we've got that there. And then the other side of the circular path will be this wire coming down here. Well, we assume that it's not starting all the way at this wire. Maybe it is, but we assume it has some finite value, so that'd be Y naught. And then it'll be moving at V naught t, so depending on what time you pick. So if you go 1 second, it might be here, 2 seconds, it might be here. So that'll give us this other dimension. So we'll have this starting point plus the additional length that it travels, so that'll be our length and our width times this B naught. And so therefore, we can characterize the EMF as simply this equation here. So we've got the voltage around the loop. It's going to equal to the derivative with respect to time of the flux. Remember, the flux, though, is that original part of Faraday's, the integral of B dot ds, but we have it now a different way. So if we take this derivative with respect to time, the only thing that varies with time is this portion here. So we're left with that. We've got it times the L and times the B naught. So this is what falls out. So this will be your voltage. It's any instance in time if you were to measure it across there while the wire is moving. So let's consider a different example. Instead of varying the loop this time, which that was an interesting thought exercise, what we're more likely to see is a time-varying magnetic field in a fixed loop. And so that would look like this. So here, our loop is fixed. So we have our z-axis and our x-axis defined here. And A is how far we're traveling or how wide the loop is on the x-axis, and B is how tall it is on the z-axis. And then we have our magnetic field is now a sinusoid. So, and it's in the y direction, so that means it's going into the page. So we would expect for this to produce some EMF or potential difference around our loop. So we can now look at the magnetic flux as defined as this integral where you're going to integrate this magnetic field dotted with this area. That's what Faraday told us we could do. And so we simply just integrate our definition of B, and it's in the y direction, and we're going to dot it with the area. So the area is going to be dx, dy, and remember the area vector is always normal to the area, so it would also be going into the page as well. And we're going from 0 to B on the z-axis, and we're going from 0 to A on the 0 to A on the z-axis, on the x-axis, sorry. And so if we dot the AYs, of course that'll give us a 1, and we're left with just integrating this part here. But the B0 cosine omega t doesn't vary with x and z. It only varies with time, so we can pull that guy out. And so now we're just integrating dx dy over a and b. And so the result of that is AB B0 cosine omega t. So then this is the flux inside of here. So this is the flux density. This is the flux, how much total flux is in there at any given time. So now that we have the flux, we can now use this to calculate the induced EMF, or the potential difference around this loop. And then to do this, we'll go back to Faraday's law, where he told us that this this EMF, which that's what this represents, the E field around the loop, is going to be equal to the time derivative of the flux, which the flux is the summation of the magnetic flux density dotted with the area vector for this space. Well, we calculated that on the last page, and we found that to be AB B0 cosine omega t. So all's left to do here then is to take the derivative of that with respect to t, and when we do, the derivative of cosine omega t is negative sine t, and so we're left with AB B0 omega sine omega t. So this would be an expression for the potential difference, or EMF, induced around this loop from our original magnetic field. So just to visualize a little bit what was happening in this problem, this would be a graph of the flux going through the loop. So you can see it is a sinusoid. It has a peak of AB B0, and it is a cosine function because we're 1 at 0, or our peaks at 0, and this would be what we expect to see from a cosine. Conversely, if we look at the EMF, or the potential difference induced on our wire, this is the wave for that, for the same time scale. And you can see, as we saw, it is a sine wave. So this is interesting to note that the voltage induced in our loop is not in phase necessarily with the flux that is going through the loop. You can see it's out of phase by 90 degrees, so there is some lag there to some degree, and of course the peak is going to be off by the frequency as well.